Hello, chemistry students. Mr. Tro here, coming to you live from A251. Today, I'm going to lead you through the 5 different experiments that are part of our Properties of Matter lab. So the first experiment, we are going to be using a substance called ammonium carbonate. So here is a vial of ammonium carbonate. The lab asks you to take some observations before and after we do the reaction. So before, you can see that it is a white powder. It's actually more of a crystal. Get a good look here. Little tiny crystals, okay? In terms of smell, I'm gonna waft the air. I'm not gonna stick my nose in, I'm gonna waft the air above it. And it's definitely got a smell to it. It's an aggressive smell. It kind of smells sterile, or like if you were to walk into a building where they just cleaned, like maybe they just mopped the floors. That's kind of what it smells like. Okay, fairly strong, but it's a white powder, little crystals. And what we're going to do now is we're going to put this into a test tube. Okay, so I'm going to take. It says to take a pea-sized amount. So picture just a little green pea, okay, about that big. And what we're gonna do now is we're gonna heat this over a Bunsen burner. Before we do that though, I'm gonna take just a minute or two to show you how to operate a Bunsen burner. So if we do come back to school later in the year, you guys will be at least a little familiar with the parts of the Bunsen burner and how it works. So this is your typical laboratory Bunsen burner. It has a few moving parts to it. It has 2 moving parts. It has this top portion, which I can screw counterclockwise, lefty-loosey, and you see that there's a gap that's created when I open that. Now we call this long piece here the barrel, kind of like if it was a pistol or a gun, it's the barrel of the gun. Okay, so if I open that up, I allow oxygen, air, to come into it. If I close it down, righty-tighty, I can close it all the way down and I can limit the amount of air that gets mixed in with the gas. Now the gas, natural gas, just like you'd have coming into your furnace at home, or maybe if you have a gas-operated clothes dryer, or maybe an oven that has natural gas, methane, is gonna come through this opening right here. And the amount of gas flow is gonna be controlled by this dial on the bottom of the Bunsen burner. So this is called the diaphragm or the valve control. Some people call it the valve. And if you look at it from the bottom, it's righty-tighty, so tight. If I go left, counterclockwise, it's gonna open up and it's gonna allow more gas to flow through. I always like to employ what I call the 2-2 method. The 2-2 method, when you light a Bunsen burner, I like to close everything down and I like to give it 2 full turns of the diaphragm and 2 full turns of the barrel. And that tends to give me a very good setting to light it, okay? You're gonna have a hose, a double-ended hose. One end of that hose is gonna connect to the Bunsen burner, like that. The other end will connect to a gas jet. Now the gas jet is at a 90-degree angle to the valve. That means it's off. So this is off. This would also be off all the way over here at a 90-degree angle. On would be in line with the valve, with the gas jet, okay? So I'm gonna have that off and I would connect the other end to that, okay? When I have this set up, I can light the Bunsen burner. Now the way we do that is we always light the match first, place it near the opening of the Bunsen burner, and then we turn the gas on, right? We do not want to turn gas on, let it fill the immediate area, and then light the Bunsen burner. That would be silly. That would be dangerous. Also, speaking of danger, I'm going to put on my safety goggles. Okay? So, I'm going to light the match. I'm going to put it at the lip of the Bunsen burner, and I'm going to turn on the gas. I can go ahead and put the match down on the countertop because the countertop is able to handle that. I'm going to turn the lights down a little bit so you guys can see what the flame looks like. So right now, I have a flame that's a little dangerous. It's pretty big. So I need to control my gas flow. I've got too much gas flow. So I'm going to turn my diaphragm, the dial on the bottom, I'm going to close that down a little bit. And you'll see that that will bring my gas flow down to a reasonable height. Okay? That seems like a decent sized flame. The barrel now. The barrel allows me to control how much oxygen mixes with the flame. Now, if I close the barrel all the way down, we get a kumbaya, my lord. Like we get an actual campfire type flame. We never want to use these. These flames we never want to use in chemistry because this will create soot on anything that we put in the flame. So it's going to leave a charred surface on anything that's hard to clean up. Here we go. Looks like 6th period is starting. But if I open up the barrel, I get a nice blue flame. So this is what we would call a cool flame in chemistry. If we asked you to use a cool flame, it's totally blue and it's just a single blue flame. If I keep turning the barrel, what you're going to see, and hopefully you can hear this too, is you're going to see a much more aggressive flame, okay, with what we call an inner cone. So you see there's an inner cone inside the flame. That inner cone creates a very hot part of the flame, so we call this a hot flame. And if you notice, if I take the match, the burnt match I already used, if I put it at the very bottom, not a whole lot happens to the match. If I put it at the very top, not a whole lot happens. I mean, it flares up. But if I put it at the cone, tip of the cone, whoa, right? Very hot part of the flame. So if a lab calls for us to use a hot flame, that's what we're going to use. This lab currently doesn't call for a hot flame, so I'm going to close my barrel back down. And I'm going to get myself a nice cool flame like that. Okay, so we have our flame, our cool flame. I have my test tube with my ammonium carbonate in it. And now I need to do experiment 1, so I'm going to put the test tube into the flame. I don't want to hold it with my hands, so I'm going to use this device called a test tube clamp. Simple design, you squeeze it, it opens up, you release it, it closes on its own. Kind of opposite of what you would think would be, so I can snap that right onto the test tube, and now I can hold the test tube safely. Now I'm going to put the test tube into the flame, put the substance into the flame. I'm going to introduce heat, and we're going to see what happens to the ammonium carbonate when I do this. Now, I want you to notice immediately, you should see that there's some sort of a vapor on the bottom there, okay? And there is a vapor that coats the test tube when I immediately put it in. It was hard to see. You might want to rewind and watch that. You can see up top right now, there's a vapor there. You see how it's all foggy, right? So there's definitely some sort of a vapor being produced. It's liquid. It's a clear, colorless liquid. And as the test tube heats up, that liquid will go away. It'll clear up. And you can see that clearing up right now as I heat the top of the test tube where it's at. So it's definitely a liquid. It's a clear, colorless liquid. And heat will make it vaporize. Now, as I continue to heat this, the lab calls for us to waft the gas that's being produced. So I'm going to very carefully waft it towards my nose and smell it. Oh, and I can tell you right now, that is extremely a very sharp smell, a very, very strong smell. In fact, it reminds me of the smell of a substance sometimes they crack it in front of a boxer's nose to wake people up. That is definitely an ammonia smell, a cleaner ammonia smell, very strong. Now, as I continue to heat it, you can see that the substance in the test tube has kind of almost gone away. There's a little bit still in there. You can see it dancing around on the bottom there. But for the most part, this substance has disappeared. And it's gone, completely gone. Now, another part for this lab, it calls us to light a wood splint and then to insert it into the test tube. So I'm going to do that. And as I insert that down in the test tube, hopefully you saw that the wood splint, the flame didn't get bigger, the flame was extinguished. The flame went out, okay? And that actually tells us something. actually tells us something about what gas might have been produced. There's a gas inside the test tube that hasn't left to go to the rest of the room. And whatever gas that is, it does not support combustion or can support burning. So in the lab, it'll tell you that that gas is either going to be oxygen or it's going to be carbon dioxide. All right, so decide based on the observations we make which one of those you think it is. You may have to do a little research on oxygen and carbon dioxide and how they respond to flame. You might have to do a little research. It asks you to do a little research about fire extinguishers as well. Okay, so that is experiment 1. Make sure on your data table you've recorded all the observations from before we did the reaction or possible reaction, and then during and obviously afterwards. Okay? Okay, we're back for part 2 of the lab. If you read the procedure, part 2 has us taking sodium chloride. Sodium chloride is otherwise known as table salt. So here's a container of sodium chloride, NaCl. Let me just focus the camera. Okay, sodium chloride. And it has us dissolving some of it into water. So I have some deionized water here, and I'm simply going to do something we've all done before. I'm just going to put some salt into water. Now I'm not going to be very careful about the amounts I use because this is what we call a qualitative lab. The amounts don't matter, okay? I'm going to use this device called a stirring rod, glass stirring rod. I'm going to mix it up like the lab calls for me to do. And if you notice, there was solid in there. As I mix it up, what we're all used to seeing is that salt, like sugar, will dissolve into the liquid. Okay, so after about a minute or so of stirring, we can see that the solid is gone from the liquid. The liquid is a little cloudy, but you can actually see through it. So we've made salt water, okay, basically. Now the lab calls for us to pour 5 milliliters of salt water into an evaporating dish. Now if you were really in school, we would use an evaporating dish because you're right there in person, it's easy to see. I'm gonna choose to use a watch glass instead. And for the purpose of filming, I believe seeing what's gonna happen on a watch glass will be a little easier to observe. Okay, so let me turn my camera. What I have set up here is a ring stand apparatus. I've got a Bunsen burner set up below, a ring stand with an iron ring and wire gauze. And on that I can place this watch glass, okay? Now I'm gonna pour a small portion of that saltwater mixture on the watch glass. And I'm simply going to turn on the flame, a nice cool flame. I'm gonna heat it. And then if you were in lab, you'd be waiting a few minutes for this process to happen. And you might actually move on to another procedure while this is happening, okay? So it might be a little difficult to see, but you should be able to see that the liquid is starting to bubble. So it's starting to boil. I don't want to get my camera too close because heat and phones don't mix, but hopefully you can see now that it is boiling, okay? So we'll just let this go for another minute or so, and we'll start to make observations then. We've already made observations of the salt water mixture that was clear and it was colorless. And now we'll see what happens as it boils. Okay, so I've taken the camera off the holder. I wanted to show you that around the edge, where some of the water has vaporized and boiled away, around the edge you can see this white coating start to appear, like an outline. You might be familiar with something similar to this in the winter. If you walk through, say, a parking lot after it had snowed and the plows had come through and there was salt that they put down on the roads, and you get your pant legs wet, after a couple hours when your pant legs dry, you notice there's a white line across your pant legs near your ankles, a crusty white line. That's the same sort of deal we're seeing here. Okay. Okay, now the liquid level is getting pretty low here, and you can start to see that there's more and more of this white crust. If you look on the edges, you can tell it's a powder. It's a crystal of some sort. Okay, now I'm going to pull away the flame because this is definitely dry now. And you can see that, oh, it just popped. It scared me a little bit. But that's because there's some trapped water vapor that made it pop. But if I were to touch this, okay, it is a crusty white solid that's left behind. Okay, it's crusted over, but there's definitely a white solid that's left behind on the watch glass. Okay, so make observations before and after. We started with a white solid, right? We started with a white solid, and it looked, just show you, right? We all know what salt looks like, but salt looks like that. And now we have a substance that looks like that. Same color, same consistency. When we put it into water, though, it seemed to disappear. And then when we boiled the water away, that white solid seemed to reappear. Okay, so this is a piece of copper foil, copper metal. You can see it's got that brownish red hue to it that you would associate with copper, like a copper penny. It's a little shiny. It's got some shiny luster to it, but it also has these streaks on it, these discolorations on it. So what I'm gonna do is I'm going to take a piece of steel wool to the copper. I'm gonna shine it up the best I can. Okay, so if I take the copper and I take the steel wool to it, and I rub the steel wool back and forth on it, kind of like sandpaper. Hopefully, you can see how wonderfully shiny that just got. If I show you the other side, there was the original copper. This is what it looks like now. Now, when we first ordered the copper, when we first got the copper sheet looked similar to this, super shiny, what you would imagine a metal would look like. But after sitting for a few years in a drawer, it takes on this hue. Okay. So the lab calls for us to find the mass, the initial mass of this copper metal. You see the one side is shine, the one side is not. I'm here in one of our chemistry labs where we have an analytical balance. If you notice, it says right now 0.000 grams. It is zeroed out. I'm going to open up one of the glass doors. I'm going to place the metal on the pan balance and give it a second to normalize. So, in your observations, right, you need to make sure you write down that the initial mass of this copper before we do any reaction with it is 3.317 grams. 3.317 grams. Okay, so the lab calls for us to place the copper metal into an open flame, a hot flame. So I don't want to use my fingers, and it's not a test tube, so I'm going to use these. They're a pair of tongs. They're called crucible tongs. All I'm going to do is simply grab the metal with the tongs, and we're going to place it into a hot flame. So let me get my camera adjusted so you can see that the Bunsen burner is in focus. Okay, just like before, we're going to light the Bunsen burner. Now, if you remember, this is not a hot flame. This is a cool flame. So I'm going to open up my barrel so that I get a nice tight cone. Now you can hear that. That almost sounds like it's angry, right? That is a nice hot flame. Okay? So we're going to take our copper and we're going to put it in the flame. Now, you can see, hopefully, on the side facing you how the color has already changed. It's no longer copper colored. It might be hard to see on camera, but it's more of a silvery gray color now. On both sides, you can see where the tongs are holding it. There's a little bit of discoloration, but this no longer looks like copper. In fact, if you went up to somebody and asked if this was a copper metal, they would probably say no. You notice the different colored flame where the flame interacts with both the tongs and the copper metal. The color of the flame changes, and that's due to another topic which we'll talk about later in the year, that deals with the metal atoms are getting excited. They're absorbing energy, and their electrons are jumping around. We don't really have the knowledge base to talk about exactly what's happening right now, but we will in the future. Okay. So now the metal's starting to glow. It's getting kind of red hot. But I'm going to continue heating it. Both sides. Notice I'm putting the metal right in the tip of that cone, nice where it's the hottest. Okay. And now, turn the flame off, bring this near the camera. Hopefully you can see that is definitely a grayish color. It's almost like a dark gray. I would say maybe a charcoal color. So somewhere between silver and black, so like a dark gray. Okay. Now this is extremely hot. So I'm going to place it into a ceramic dish. I'm just going to let it cool off for a few minutes and we'll come back. It's cooled down, and you can see that during the cooling process, there's been like a flaking of the surface, a curling up of the surface. I don't want to turn it over to show you the other side yet because I'm afraid these flakes might fall off, but I'm going to put it on the scale gently. And we can see a new mass now of 3.404. 3.404 grams. So make a note of that in your final observation part of the data table. Okay, so as I stated a little earlier, there appears to be almost a flaky surface to this copper metal, and you can see that if I can actually scrape away, so the surface of the copper almost created, if you look, it's a dark gray, almost black, brittle, very brittle. It breaks up when I touch it. Substance. Now that is not copper, because copper, first of all, is copper colored, and copper is not brittle. Copper can be bent. It's very malleable. It can be shaped. It doesn't break up. So this is definitely a new substance that's created. Not exactly sure what it is, but if we were to scrape that outer layer away, we still see that it doesn't look like copper underneath. It's this off color, this light gray color. And so I'm going to take a file, an iron file, and I'm just going to scrape away this outer layer. So as I do that, hopefully it's showing up on the camera. As I scrape away, you're able to see that underneath that outer layer, that exterior layer, where we reacted it with the flame, underneath it is still copper colored, okay, and nice and shiny. Wonder if the same thing's true of the other side. The other side, if I take the iron file and I scrape it, same thing happens. Once I get through that outer layer, I get to that shiny copper layer underneath. Now, you can see on my fingers that the outer powdered layer is indeed that. It's just a powder, flaky, very brittle substance. So something has happened here when I reacted this in a flame. Now, the flame is not a reactant. Flame is just energy. But the flame must have provided the energy needed for this copper to react with something in the air. And if you think about it, there's only a couple things in the air that are of substance. Nitrogen is about 80% of the air, and oxygen is about 20% of the air. Every other gas you can think of that's in our air, like carbon dioxide and hydrogen and helium, they make up way less than 1%. So this must have reacted with either oxygen or nitrogen in the air and formed some sort of a new compound on the surface. Okay, we're here for part 4 of the lab. Part 4 of the lab has us taking an Alka-Seltzer tablet. The lab calls for half a tablet, and that's mainly because we want to conserve on our materials when we have everyone in class, but since it's just me here, we're going to use a whole tablet. Okay, so there's a whole tablet of Alka-Seltzer. I've got myself a beaker of water, and then we're just going to observe before and after. So obviously before, we have a clear colorless liquid in water. We have an Alka-Seltzer tablet is a white solid. It comes off and kind of scrapes off of my finger, so it's a white powder. And we're just going to pop it in to the beaker. And you can hopefully see that immediately there are bubbles. Okay. There were not bubbles before, but there are bubbles now. And the tablet is reacting. It's hard to see from the camera, I know. But if you look at the bottom through the glass, hopefully you can see the tablet is kind of bubbling away. There it is against the side there. I don't know if you can see that. There, it's a good shot. Okay, it's just kind of bubbling away. The liquid appears to still be fairly clear, but the tablet has pretty much disappeared. So a gas was produced. No significant change in temperature, but there are definitely bubbles of gas, and there wasn't gas before. So this process generated gas bubbles. And there's a little bit of residue on the sides. But there you have reaction 4. Okay? Make your observations of before and obviously afterwards now. Solid has disappeared, and you have a liquid that we call this carbonated, a liquid that has gas trapped inside of it. And you can see that the gas is actually releasing slowly, kind of like if you were to open up a pop can and let it sit for a few minutes. This is kind of what it would look like. Okay, and now it's time for our 5th and final procedure of the lab. And it has us mixing 2 substances. This says 0.1 m. We'll just disregard that for now. That's just a concentration, tells you how strong it is. But the substance is iron chloride, FeCl3. You can see that it appears like it might have a color to it, but we don't want to take the color out of one of these bottles. This bottle has stored this substance for a long period of time, so the bottle might be stained itself. We also have a bottle of silver nitrate, AgNO3, and this bottle you can see is also stained very severely. So what I want to do to take true observations is I want to put these substances into test tubes, okay? So iron chloride, I'm going to put a few drops or a small squirt into the test tube on the right. And you can see that it is a yellow, clear liquid. We call this a solution. It's a mixture. The iron chloride has been dissolved into water, so it's an aqueous water-based solution, so it's yellow in nature. Now to the other test tube, I'm going to add silver nitrate. And you can see that this liquid, contrary to what the bottle might appear, because the bottle is very stained, this liquid has a slight tint to it, but for the most part, it's a clear liquid. Okay, so we've got a fairly clear liquid, and we've got a yellowish liquid. And what we're going to do now is we're going to mix the two together. So I'm going to pour the two together into this central test tube. Let's see what happens. And you can notice that the mixture of the two, when the two are mixed together, you get a definite color change. Okay? Definite color change. So make observations on what you see. There's a white solid floating on top of that test tube. There was not a white solid before we started this process, but there's a white solid now, okay? And the rest of it is this murky, whitish yellow color. I'm gonna pour a little bit of it out onto this watch glass so we can get a better look at it. And hopefully you can see that it's a murky liquid, but there's definitely solid floating around inside where they were mixed together. We didn't start with any solid whatsoever. We started with two liquids that were no solids involved. And when these were mixed together, there was a color change and there's a white solid that was formed. Okay, so that is all 5 of the procedures that were listed for this Properties of Matter lab. You need to make sure that if you didn't catch it the first time, you go back and rewind and rewatch the different processes and make sure in your data table that you have initial observations before any mixing or any reaction or any procedure was carried out. And then you also make observations during a reaction if it's applicable, and then definitely observations for after a reaction. And then by comparing what you see before and what you see after, there are clues that tell us whether a chemical change has occurred or a physical change has occurred. Now, just to review, before you move on and work on this on your own, a physical change is not a change in the identity of a substance. So if you start with a substance and you end up with the same substance, but maybe it changes form, like tearing a piece of paper would be a physical change. Bending something would be a physical change. If you start with the same substance and it was there at the end, and I can think of at least one procedural example where we started with something, it appeared like it changed, but it was still there at the end. That would be only a physical change. However, if you start with substance A and then you do a process to it, and what you have at the end is a new, different substance with different properties. Maybe it's a different color. It's instead of being hard and shiny, now it's flaky and brittle, right? That would be an indication that the substance has changed into a new substance. And when you have a change to a new substance, that is called a chemical change. And we actually call that a reaction, a chemical reaction. So use your notes and obviously use the data from the lab to try to figure out which of these 5 reactions or which of these 5 processes is a chemical reaction, a chemical change, or just a physical change. Okay? Till next time, see you later.